Welcome back to Street Talk. Today's episode is going to be presented by my partner in crime, MIT PhD, Dr. Keith Duggar. Go ahead, Keith.
The concept of probability as something more than a frequency reaches far in human history.
The ancient Greek philosophers referred to eikos, which Socrates described as likeness to truth, which set it apart from truth, which to Socrates was only that which could be deductively proved by logic. Yet our journey towards a more general concept began with frequencies and games of chance, as gambling has long enthralled our species. For 2,000 years after Socrates' time, humanity inched its way slowly through logic and mathematics, until the mid-1600s when the great French mathematicians Fermat and Pascal put forward the beginnings of a modern mathematical theory of probability. Over the next 100 years, probability pushed a little bit forward to problems of so-called inverse probability, helped along by none other than Bayes himself. Finally, in the early 1800s, Laplace generalized probability beyond the scope of gambling to scientific inference, where it reigns supreme to this day even at the most fundamental bedrock of the universe, and perhaps even of mathematics itself. As James Clerk Maxwell of physics fame said, "The true logic of this world is to be found in the theory of probability." Given the hard-won progress of human thinking to rise from frequencies and games of chance to a more general and more powerful concept of probability, why then do we seem to slide backwards in the early 1900s, only to slowly recover at the turn of the century? I think there are two important drivers for that. First, solving actual models of physical systems can be hard, if not impossible. Just look to the many simplifying assumptions or system simplifications required to find solutions in, for example, general relativity or quantum mechanics. When we deploy probability theory's logic, it often demands of us computations that we simply could not realistically perform in those early decades of the 20th century. So applied mathematicians and scientists naturally turn to simplifications they could calculate, i.e. they turn to statistics. Second, at the same time, a dominating and belligerent, according to some, personality arose in the field in the form of British statistician and geneticist Sir Ronald Fisher. The useful application of statistics to his field of genetics, combined with the force of Fisher's personality, created a gravity well that sucked entire generations of scientists into a limiting frequentist orbit. Of course, as fellow British statistician and chief executive of the Alan Turing Institute, Sir Adrian Smith put it, any approach to scientific inference which seeks to legitimize an answer in response to complex uncertainty is, for me, a totalitarian parody of a would-be rational learning process. In other words, at some level of complexity, at some level of reality, statistics is doomed to break down and force us up to the mathematics of uncertainty itself, in other words, probability theory, and its tools of analysis, such as Bayesian analysis. This is why many practitioners, such as Connor, Alex, and myself, are ultimately driven to Bayesian analysis to surmount the many practical challenges that confound the limited scope of statistics, such as model selection, small sample size, few-shot learning, combining experiments, incorporating prior knowledge, non-normal models, etc., etc. Luckily, the development of Bayesian methods over the last century hasn't entirely stagnated. New theoretical developments in such fields as information theory, differential geometry, and even theoretical physics, as well as the advance in applied methods such as kernel methods, empirical Bayes, and Markov Chain Monte Carlo, combined with ever greater computer power at our fingertips,
have finally set the conditions for Bayesian methods to rise again and indeed thrive over the next century. We hope you enjoy the ride. Hello, hello, Machine Learning Street Talk. I'm Dr. Duggar, and together with my compadres, Dr. Tim Velocity Video Scarfe and Alex Bayesian Social Stenlake. And in our guest corner today, we have Connor Tann. Welcome to the show, Connor.
Hello, thank you so much for having me.
So Connor is a physicist and senior data scientist working for a multinational energy company where he co-founded and leads a data science team. He specializes in the application of machine learning models with a particular passion for probabilistic models and everything Bayesian. He holds a first-class degree in experimental and theoretical physics from Cambridge University with a master's in particle astrophysics, of all things. As we are all Bayesian enthusiasts here, we are going to probably take the opportunity to go deep down the rabbit hole, but you never know, on many important subjects in the Bayesian arena. For example, model selection, one of its most important applications. So yeah, Connor, welcome to the show.
Thank you so much.
So tell us a bit about your interest in Bayesian methods. How did you come to those, if you will, in this era?
I think I'm probably quite a late convert, actually. So I think, like a lot of scientists, I was taught frequentist all through education. I learned general statistical methods, hypothesis testing and t-tests and so on. And then get into the real world. It was hard. It was so hard to make all of these approximations work. It was so hard to predict the things I was trying to predict. I think probably my first exposure was working with a really, really great colleague, a physicist called Anjum, who would write these reports. And when I expected some kind of hypothesis test to happen, he'd always have something about sampling and some Markov Chain Monte Carlo and a burn-in period. I had no idea what on earth was going on. And then his results always matched much, much better with kind of common sense than what a frequentisting approach would lead. And so that got me interested. And that was several years ago. And now it's just, I guess my eyes were opened. I saw the light.
So you were really driven by practical considerations. You were just trying to solve problems, and the tool set that you had wasn't working out for that. And that's kind of what pulled you into this Bayesian arena. Fair to say?
That's exactly it. I think it was also working with small data sets. That was really the key.
Right.
So where there were cases where I had very little data and a lot of physics-based knowledge, a lot of science that tells me what should be going on. And I just need some way to combine multiple sources of information.
I'm going to be asking all the dumb questions today, but can you explain to us, like we're five, what the benefits are of Bayesian approaches?
Definitely. Okay, so I think the biggest benefit is being able to capture your prior beliefs. Using a prior probability function. So for lots of times when you see new data and you immediately forget everything you know about the world and you try to analyze just what that little bit of information is saying. But most of the time you care way more about the full picture. You've got lots of past experience. And so doing your knee-jerk reaction of just kind of myopically focusing on the new data gives you the wrong result. And that's what Bayesian stats gives you over traditional methods. It helps you kind of use your common sense, bring everything you can to the table, everything you've seen before, and make the most of your new data as well.
There is an interesting continuum though, right? Because if you just want to get stuff done, the frequentist methods just give you an answer. And with these Bayesian methods, you get more information. You get confidence intervals, for example. But in practice, is that useful?
You get confidence intervals with frequentist methods too. It's just the interpretation of those confidence intervals aren't always as naturally interpretable as they are with Bayesian, like credible intervals or, just a histogram of your posterior.
Well, on that, so if you make bare predictions with a frequentist method, let's say a support vector machine or something, or even a neural network, you get an output, and typically you scale the output. You might use a sigmoid activation or something. So you might get a number between 0 and 1. And it's a little bit weird, isn't it? Because you get these kind of asymptotic flattening edges on either side of the function. And you could make the argument that if it's a binary classifier and you want to say yes or no, then the closer it is to 1, the more confident you are. But that doesn't really work very well. And there are approaches, like there's something called the transductive confidence machine, which is a way to introduce confidence measures into traditional machine learning methods. And they compute a measure of strangeness, and you compute multiple predictions, and then you run it through something that looks a bit like the Bayesian function to give you these confidence intervals. But I would argue that with these traditional methods, you don't really have confidence intervals.
Well, let me point out something, which is because you mentioned kind of, and I'm even forgetting what you called it now, but some transduction, whatever. I think the important thing or point I want to make is that that's all arbitrary hacked stuff. Okay, like just think about it in the machine learning world. When somebody comes along and goes, hey, I'm going to add this cool new layer that nobody's ever thought of, and wow, look at that, it works great. That's, it's just a total hack that they pulled out of thin air, or maybe they tried 1,000 different things and then, only magically shared the one that worked. The interesting thing about the Bayesian approach is it's derived straight from probability theory. I mean, it's just, if you take the product rule of probability theory, the conditional product rule, right, which says the probability of A and B, so the logical conjunction of A and B, it's equal to the probability of A given B times the probability of B. That's it. That's the product rule. And actually, just from that rule alone, just by swapping the symbols, you automatically derive Bayes' theorem, right? I mean, to deny, for example, Bayes' theorem is just to deny the product rule, which is a bit of a problem because nobody denies the product rule, right? And the product rule automatically gives you this capability to chain, if you will, or to reason about multiple sets of data, like Connor was saying. If we know that this distribution is exponential or something weird based on a physical model, how do I incorporate that knowledge? You automatically get that capability through the product rule of probability theory. And so the unique thing about that approach is it's the only one for which we actually have a very firm, agreed upon mathematical basis, as opposed to people coming along and saying, oh, do batch norm because it magically works or something, but we don't really have any theory for why that works.
I've got to say, though, in defense of hacks, I think there are so many things that machine learning engineers have done just because it works. We don't really understand why it works. And sometimes, retrospectively, you can then derive them as actually, if you take a Bayesian framework, you can reason why this is the right thing to do. So I think my favorite example is regularization. Mm-hmm. So suppose you're fitting a big linear regression model, for example, and you've got all these terms, and your model is really overfitting the data. So what you do, you think, well, curve fitting says that this is my best equation, but I'm just going to dampen down all the parameters. I don't really want any large numbers, so I'm going to just add an extra term, some of the squares of all the coefficients in my model, and that's just going to give me a model that uses fewer, predictive variables. It's going to be a simpler model, and I just reckon that's going to generalize a bit better.
I think that's
how it first came about.
There's that old saying, if it works, it's probably because it's Bayesian deep down. But deep down, I think that's probably just a bit of, Bayesian elitism coming in, the Bayesian board absorbing all, models as a special case of their own. But you are right.
That case said that if you have a prior, so regulation, you can derive that if you assume it's a Gaussian prior of your variables, right? If the L2 norm corresponds to having a Gaussian prior, I think having an L1 norm is a Laplacian prior.
But even on that, because you could argue that regularization, sometimes it's enforcing a simpler model, sometimes it's just making it harder to learn. Like with dropout in deep learning models, you're just randomly zeroing things off during training.
Well, that's because the fundamental problem that we're trying to solve is this requirement that you have to do these unsolvable integrals. They tell you that if you really want to solve your problem, you have to conduct this marginalization, and we can't. There are these like vast multidimensional integrals, or even worse, they're mixed integer integrals or combinatorial integrals, and so like you're bringing out dropout layers. The problem is that we can't do the integral that would tell us, look, you only need these 17 nodes out of the 100 that you're sort of having in that layer or something. And so we just sort of randomly explore that space and try to find it. But ultimately it comes down to the fact that we can't conduct these integrals efficiently.
Just on that subject of priors, we spoke to Max Welling recently, and he made the comment that there are always assumptions in all models. There are always priors. Even in the kind of frequentist models that we use, like deep learning models, there's this bias variance trade-off, right? And he was saying that if you introduce more inductive priors, then it actually makes the approach a little bit more sample efficient, because you're basically making assumptions about the type of data that you're going to experience. It's not so different to the Bayesian methods, but there are some interesting things, because you said, well, at some point everything is Bayesian, and that certainly seems to be the case with, let's say, kernel ridge regression, right, which is a kernelized and regularized form of least squares. And it turns out that you can do this Gaussian process thing, right? Why are they equivalent?
Well, a Gaussian process isn't necessarily equivalent to kernel ridge regression. It's just, if you start from kernel ridge regression, it's possible to get closed form estimates of your uncertainty. And like, really, okay, let's put on the stack this idea of uncertainty and Bayes, because that's kind of the practical upshot of Bayes. But kernel ridge regression, estimating the mean function from memory, is the same in Gaussian process. It's kernel ridge regression in a Gaussian process gives you the mean function, but there's also this measure of like what you don't know, and that's where it gets different from traditional ridge regression. The way that that's calculated is different, and admittedly, there are ways where if you have a linear kernel, it is the same thing as Bayesian ridge regression, and you avoid cubic calculations, and it's all much neater. But then you don't get the nice nonlinear stuff, and the universality of the Gaussian kernel and stuff like that.
It's funny you mentioned Gaussian processes. I guess it turns out that in business, we often care a lot more about the uncertainty in a prediction than the actual prediction itself. So there are many times when one particular model might give you the best possible answer for something like a Gaussian process that can really neatly describe, give you a standard deviation at any given point, can really nicely summarize the uncertainty. It's just so more useful for decision making.
It's important to realize how much the language of a frequentist, view has kind of permeated, through all the concepts that we talk about. For example, the idea of bias to begin with is not a Bayesian concept. It's like when you do, what Bayesian tells you is that if you have a model and you go and collect some data, okay, after you collect that data, the sum total of everything every iota of information that can come from that data is actually represented as a distribution, not as a number, not as a statistic, not as an estimate, right? Those are all, you end up with this distribution that tells you everything, the totality of all the knowledge you have. And when you reduce that to a number, to a statistic, i.e. to a function of it, that's when you cross over into the world of statistics and you start to get into all these issues of like, well, this one magic number that I chose from this distribution, like the mean or the mode, right, or the median, has all these issues, right? Yeah, because you've taken the information and you've compressed it into a single estimate. And so like what Connor's getting at there is that, in business, you care a lot more actually usually about that distribution of knowledge and how that can affect your outcomes considering different scenarios than you do about just one particular arbitrary, summarization of that distribution.
Let's work through an example of that. I mean, in a second, Connor, it'd be great for you to introduce what Gaussian processes are. But what we're talking about here, though, is that with kernel ridge regression, it would predict a number given a signal. And with Gaussian processes, as well as having the actual number, which is basically the mean or the mode of this distribution, we also have some measure of how certain we are. And you asserted, Connor, that that's super useful. So can you give me an example of when that's super useful?
I think often it comes when you have the ability to collect more data in future and you're trying to understand where do I take new measurements if I'm, or do I even need to? And so it comes to informing decisions where especially if you're a scientist or engineer, you're trying to model something. Having a most likely estimate of any given property really doesn't help you with very much at all if you don't know if you can trust it, and you don't know if you need to do more work to refine that estimate. So I think in in my career so far, probably the biggest impact has been in understanding how we can target future data collection by looking at where there is large, where it's small.
Right.
And how you can combine disparate experiments, right? Like you have one experiment that gives you an estimate with this range and a completely different experiment that gives you a different range. How do you combine those? You need a mathematics to combine those. And that mathematics is probability theory.
So am I getting that? So the most important reason is we might have irregularly sampled data, and it gives you an indication of, first of all, it's more efficient because it means we don't need to uniformly sample. There might be some areas where we're not so sure where we need to focus our energy. And Keith, you were saying that there's also a compositionality component here.
Yeah.
Yep.
So something that's often like not well understood. People come across priors and they think, well, we're just kind of injecting our subjective knowledge and blah, blah, blah. You're biasing your results. But really, it's not just, subjective knowledge. It's things like, what do we already know? So that can be the outputs of a previous experiment. You can use it to update your results. You can also extend this to this kind of wild class of extended models called hierarchical models, where you assume, say, the classic example here, and apologies to anyone out there that's sick of this example, but it's probably the most intuitive one. It's called the 8 schools example. And okay, the experiment looks like this. We want to design an educational initiative. We want to figure out if a program helps kids improve their grade, right? And we test it in 8 schools. Now, we want to know, we know that schools aren't the same. We know that schools are in different locations. Maybe some of them are better funded than others. We don't expect the result to be the same across all of these schools. In classical statistics, we can kind of address this in one or two ways. We can say, okay, let's just pull it all together and get some mean estimate of response, right? Or you can treat each school individually and not really and not really have any way to generalize beyond these schools. It will be an accurate model, but it won't generalize well. It turns out within Bayesian statistics, you can view these schools as kind of drawn from a distribution of schools. And in that sort of framework, and this is a very natural extension, you just sample from a distribution of school and then sample your students out and maximize the likelihood of that model. And then what that really allows you to do is kind of get an in-between result where information is shared between schools, right, to an extent. Philosophically, what we're saying, more mathematically, what we're really saying here is originally we assumed there was a standard deviation of 0 between our schools. When we do our full pooling, we assume there is no difference between them, standard deviation 0. When we don't compare at all, that's equivalent to the standard deviation is like infinite case. If we relax to that very large sort of nice area in between 0 and positive infinity, then we get this natural extension that shares information and allows estimates in one school to constrain estimates in other schools, thereby lowering our uncertainty across the board. Well, not necessarily lowering our uncertainty, but properly quantifying it, giving us a good idea of if we were to extend this program to a new school, what our range of outcomes would be that properly incorporates the uncertainty across the schools that we have and the uncertainty within the schools. Cut take. That was a long one. Sorry.
That's a great example. It reminds me of I think it's a famous misinterpretation of statistics in America. I think it was about class sizes. I'm sure you've heard of this one already.
Tell us.
But there was a phenomenon that schools in rural areas, well, they had all the best performing schools, all the students that had the best average grade, ones that got the biggest percentage of students getting into the best universities, they would tend to be in these rural areas. And so there was this, we were racking their heads, why could this be? Is it something in the air? Is it getting outdoors? Is it nature? Is it small class sizes? Could that be it? And there was lots of government policy to try and make more schools like these schools. And then people also eventually realized that the worst performing schools were in these rural areas as well. And it was just about small class sizes. And if you if you take the kind of naive approach that Alex was referring to, of just treating the schools as completely independent, then it's quite easy to reach a very misleading conclusion. But if you build a proper hierarchical model, and you create, calculate some credible intervals, you recognize the fact that there's just going to be a lot more variation in the smaller class sizes. That's why they've got lots of the best classes, lots of the worst, just because they're more variable, because of a smaller number of students. And then you realize there's nothing at all going on about being rural or urban. It's just about
this might be a good thing to contrast with frequentist approaches. So you're saying that in rural areas, classes which are small are more variable. So if I was a frequentist model, presumably I would just incur a lot of error because there's so much uncertainty there. I would make a lot of mistakes. Whereas with the Bayesian approach, you would realize that there's a lot of uncertainty there, and that would be a cue for you as a data scientist to kind of double click on that uncertainty and look for more information.
Yeah, that's right. So it is very possible to model that all correctly with a frequentist view. There's nothing stopping you from doing that. But I think it's the Bayesian approach leads itself more naturally to kind of handling that kind of hierarchical situation.
Yeah, you can formulate it in terms of like a mixed effects model, and it will work, but philosophically it doesn't make a lot of sense. And I guess it really comes down to that idea of, are we going to start from a blank slate every time, or are we going to incorporate something we know about the structure of the problem? And if you're incorporating things that you know about the structure of the problem, and inevitably you are, you're choosing a linear model, you're incorporating information about the problem, then you quickly find yourself philosophically in Bayes land, and you kind of have to lean into that. If you don't, then you kind of like half the time with frequentist stuff anyway, you're invoking multiverses or infinite reruns of history to justify the extinction, whether or not the extinction of the dinosaurs happened. But and so it sounds dumb, but like, how you can't explain non-repeating events within a frequentist framework, whereas Bayes handles it naturally.
Go on, give us an example of what you mean.
So one of the classic examples of this. So I think one of the first real Bayesians, if you will, I think we should keep in mind that Bayesian statistics, if you will, or really probability theory, was the original concept of probability theory. Okay, it wasn't until R.A. Fisher, with his sort of dominant personality and belligerent kind of attitude to everybody, forced kind of generations of scientists to fall into the kind of frequentist, mindset, right? So, but way back when, one of the first kind of, people applying these rules to science was Laplace. Okay, and so when he went and estimated, for example, the mass of Saturn or whatever it was, and he ended up with a distribution for that. Well, the mass of Saturn lies between X and Y with a 95% chance. Okay, to him that just meant that his state of knowledge, the certainty of his state of knowledge, was this confidence interval, right? And to try and imagine some type of ensemble in which that's a frequency, you have to try and imagine, well, in some multiverse, like 95% of the time, Saturn has a mass that falls within this range, right? Because that range is larger than whatever your experimental error is on your telescopes or whatever you're measuring. That variance is there because of physical sort of considerations and modeling and uncertainty, right? Not error. There's no error source that gives you that range. And there's no reasonable ensemble in which that range is a frequency. It's a state of knowledge. And you can take this extreme even further. So, Richard Cox, a physicist, I think an American physicist, wrote a paper long ago in like the 40s or something, which was this fantastic, very objective look at the difference between frequentist and kind of, probability is a state of knowledge thing. And you can go so far as to consider constants, like scientific constants, like say the fine structure constant. If we have an experiment that says it lies within this range and another one that says it lies within this range, and we have this confidence interval, what are we imagining? Some ensemble of universes in which like this mathematical construct, this quantum mechanical thing, like takes on different values, right? Of course not. Like it just doesn't work.
There are definitely contexts where the frequentist approach makes perfect sense. Like if you want to calculate the outcome, like if you're gambling,
Sure.
right? One of the great hobbies of all probabilists throughout history, gambling. Frequentist inference makes great sense because you start another game and there's your repeated outcome. You do this again and again with respect to rolls of the dice or draws of cards. It makes perfect sense completely. But Bayes isn't really a way of estimating statistics so much as it is a logical framework for updating one world state to another. And you can do that in the context of one event. You don't need to define a probability in an infinite run of events. You can just have a single event there. Whereas frequentist statistics, to kind of do away with the prior, kind of has to assume this infinite run and these limits, which is fine, but it does break down in that sort of weird middle ground where n is less than a couple of 100,000.
What do you mean going from one world state to another? Because my understanding is you're updating your prior beliefs.
Yeah, sure, but okay, we can do this in terms of single flips of coins. Right? I have a coin in my hand, say, and is this a fair coin? We're going to start by assuming that it is a fair coin. We have a model of the probabilities of a fair coin. We flip it, we observe something, and then in the beginning we're probably going to have a fair belief that it's a fair coin, and so one single flip's not going to affect our posterior probabilities too much. However, if I keep flipping this coin and heads is coming up about 80% of the time, then over time, our beliefs will shift away from this being a fair coin to being a biased sampling process. And, we can do that instance by instance. We don't need to look at hundreds at a time and then get some kind of measure of central tendency. We can just, in a simple problem like this, we can just directly update the posterior in we won't go into conjugacy, but basically, because it's the same form of a particular model, that's a nice, easy one. We just bump up a number by one, and our posterior is updated.
It's a great example, actually, I think, of how a Bayesian approach gives you a more common sense answer that's just easier to interpret than a frequentist one. So if you're flipping coins and you want to work out, is this coin biased? Well, in a frequentist point of view, you can work out what is the probability that I falsely claim that it is biased, even though it's not actually biased, so a type 1 error. Whereas a Bayesian interval will tell you the probability that it's biased, whether or not I assert it's biased or not. It's just a lot more related to what I actually care about.
Could you talk us through the intuition here? So let's say we start off with a binomial distribution, which is just a kind of binary distribution of heads and tails. We start off reasonably believing that the coin is fair, so it's uniform. And then you do a bunch of trials with this unfair coin. And talk me through this. So you're measuring it, and at some point it kind of converges on something which doesn't look fair anymore, and you update your beliefs. And I think one of the ideas of Bayesian approaches is parsimony. So with not many trials, you should be able to reason about your belief that it's unfair and how unfair it is. So how does that work?
Well, let me. This is one of my favorite examples. Okay, so I want to field this for a minute. Okay, because fair coin. All right. So the model is we have this stochastic process, right? And it's like you said, it's this Bernoulli process. We're sampling it now. Either it gives us heads and tails equally with a probability of 1/2. Okay, or it doesn't. By which I mean it gives us heads and tails with some other probability somewhere in the range between 0 and 1, right? So the hypothesis or the statements we're trying to figure out here are the probability that f exactly equals 1/2, or the probability that it equals something else between 0 and 1. Now, if you Google right now, anyone out there, Google fair coin, and I hope after this video the web page doesn't get corrupted or hacked or something. But if you Google right now for fair coin and go to the Wikipedia article and read the article on fair coin, nowhere in that entire article does it have probability f equals 1/2. The entire discussion is about what's the distribution of F? Does it lie between this range and that range? Why? Because frequentists have no tools by which to answer this very simple question of comparing two models. Model 1 has no free parameters. It's F equals 1/2. Model 2 has this free parameter F, which can be any value between 0 and 1, right? This is what we're trying to answer. We're not trying to figure out what's the probability that I flip 256 heads in a row, if it's 1/2. What's the probability that F lies in some range? We're trying to answer this what seems to be a very simple comparison. Is it 1/2 or does it lie somewhere between 0 and 1? And a Bayesian framework gives you a tool set to answer that, but you have to do this integral. So if everybody knows the equation, like, all right, if I've got H heads and T tails, then the probability distribution of F, all would agree, like a frequentist and a Bayesian would all agree that probability distribution is proportional, and here F is the fraction of heads, is proportional to F to the H times 1 minus F to the T. Okay, everybody agrees that's the likelihood function. Okay, now what do you do with that? Well, a Bayesian tells you, okay, if I'm comparing these two models and one has a free parameter, I have to marginalize that free parameter, i.e. I have to conduct this integral from 0 to 1 of that equation, right? And you can do that integral. I think it's called like Euler's integral or something. And you need to have a prior for F, right? And you can choose whatever, uniform prior, Jeffreys prior, Box and Towels prior, which is like the square root of Jeffreys, whatever you want. Okay, it's not going to make a big difference. It's going to amount somewhere between having measured a single data point and no data points, okay, prior to this experiment, if you will. So you conduct this integral and you get this thing, which is a bunch of factorials, okay? And that actually gives you the probability that it's not equal to 1/2 versus 1/2. You can calculate this and you get a number. And every time you collect a data point, that number changes. And you can do something very simple, which is to say if that's less than 50%, in other words, it's more likely that it's biased or not biased, you can come to a conclusion about whether the coin is fair or biased. And my point is that, p-values and all that kind of stuff do not answer this question. They don't answer that question. And frequentists don't have a toolbox to answer that question.
That reminds me of, I think it was the hypothetical thought experiment that Bayes first proposed, I think, to explain Bayes' theorem and why it was needed. Very similar, working with a binomial distribution. But he considered a pool table where you had a game that would play, and you'd roll a ball, a black ball, onto the pool table, and you wouldn't look at where it landed. Then you wouldn't worry about the pockets or holes. You assume the ball stays on the table somewhere. And then you roll a series of red balls onto the table. And you might say, if a given red ball falls to the right of the black ball, then I get a point. But if the ball rolls to the left of the black ball, then you get a point. So a very simple game. And you can work out quite quickly that the probability of winning a point is just a fraction of how far along the table is the initial black ball. So if the black ball starts in the middle, it's a fair game. If the black ball starts off 90% to the right, then one person is a lot more likely to win the next points than the rest.
What are the assumptions there? So, for example, is there a distribution of velocity that I hit the ball?
The assumptions there is that a ball just gets placed uniform randomly from left to right on the table.
Oh, sorry. I thought you meant it got hit.
Nah, there's no collisions, no pockets. We're just randomly throwing balls onto a table. Yeah. So the interesting question is, let's say we've played a few rounds, a few points, and let's say I've won 2 points, or maybe I've won 2 points and you've won 1 point. And that's all you know. So you haven't actually seen the balls. You don't know where they've landed. You just know that I've won the first 2 points and you've won 1. What's the chance that I win the next point? And so most people, by common sense, just think, well, maybe Connor's won twice as many points, so maybe it's like 2/3 to him. If I've won 99 points and you've won 0, you're very confident that I'm going to win the next one because that black ball must be all the way over in my corner, that initial first black ball.
And this is analogous to what Keith was saying before when he said, frequentists would just say it's 0.5.
Well, it goes back to actually to what Alex's point earlier on conjugacy, there's a lovely solution to it. So your gut instinct often says, well, I'll just add up our scores, and Connor's score divided by the total, that's his chance of winning. Tim's score divided by the total. But that breaks down when you haven't got many points. Like, what happens if I've won 1 point and you've won 0? Am I 100% likely to win the next point? That doesn't really make sense. You've got very little data. So instead, if you solve it with the Bayesian point of view, you can say, well, I'm going to assume that the black ball is somewhere, a uniform distribution. And then it's this very simple example. I'm just going to update that distribution, slightly towards Connor or slightly towards Tim with every ball rolled. And it's a really neat solution. You can model it as a beta distribution, which is just a distribution between 0 and 1 that can be kind of swing one way or swing the other way. And the answer, it's as if we were just to add 1 to both of our scores and then use that old approach. So if I've got 1 point and you've got 0 points, then the way I work out my chance of winning is I take my score plus 1 and your score plus 1. So it's 2 to 1. And I've got a 2/3 chance of winning the next ball. So you can do it in your head. It's that easy.
And by the way, that's exactly what when I kind of said earlier that a good prior is worth maybe 1 data point. It's exactly this that I'm talking about, which is a lot of times if you choose ignorance priors, and let me say up front that quantifying ignorance is a very difficult problem. There's a lot of unknown, a lot of ongoing research about how to do that effectively. So I'm not saying this is a solved problem, but it's not a problem we should sweep under the rug and ignore, which is what sort of like, frequentists would do, right? They just ignore it and make some assumptions and don't tell anybody. Let me just finish here. But it's that if you use these kind of ignorance priors, what you often end up with is exactly what Connor's talking about there, which is they have this kind of conjugacy in the sense that prior is equivalent to some number of data samples that you might have observed. Like in the case of the coin, the Bernoulli trials, the coin flipping. If you use a completely kind of ignorant prior, which is this weird, like, improper 1 over f, 1 over f times 1 minus f. So the reciprocal of what you would see in like the Euler integral, with 1 data point each. That thing forces you to observe that heads and tails are actually possible. Like it assumes that it might be possible that the coin is just 2-sided heads or 2-sided tails, and you need proof that that's, not the case. Whereas, you can get to kind of the uniform prior, which is what Connor, the result there is that it adds 1 to both of the data points. So it's kind of equivalent to having observed, that you had achieved at least a head and a tail, so that a head and tail was possible. So the priors have like this, very kind of minor effect in one sense, which is they're worth just a data point or 2 or something like that, right? If they're good. And we're talking about ignorance priors. But the really cool thing is kind of what you said, Tim, which is, well, what happens if I know if there's a distribution on the velocity? Like when a person throws the ball, they're doing so with a certain velocity. Okay, like how do I incorporate that? Well, guess what? You need a tool set to do that, a mathematical tool set to do that.
Yep.
And the Bayesian framework gives you that tool set. It lets you incorporate all these kind of wacko models. Like here's my velocity model, and here's a trajectory thing, and it can be complicated. And then it gives you the tools to compute with that. It may be a very difficult computation. You may not be able to do it on computers without a bunch of approximations, but you at least have a tool set to incorporate that prior knowledge.
So I'm going to ask a couple of dumb questions because I'm the only non-Bayesian here. Now, with the beta distribution, it sounded like you were saying, I'm going to update my beliefs around the score as we have new information. Now, that seems good because every time someone's score updates, that information is incredibly useful. But you also start out with a uniform prior on the ball positions. And that's a situation where if you update that, I think it would get less accurate. Because if you play 5 balls, having a uniform distribution, we already know that it will converge asymptotically to that uniform distribution. So surely that's better, right? And what Keith was saying about the velocity of people throwing the ball in, that's another one of those weird situations. Perhaps you can explain this, Connor, that we assume it would be normally distributed, and the universe just naturally gives us these normal distributions. Why is that?
So, interesting question. So, a uniform distribution between 0 and 1, so a flat line, it's identical to a beta distribution with parameters 1 and 1. So they're completely equivalent. One reason, though, you might write it as a beta distribution is that it's very easy to update. You can skew it one way or skew it the other way by changing those parameters. So it may sound confusing that we go from a uniform to a beta, but in fact, it was just a special case of a beta all along. And then when you have lots of data and you have a distribution that's very peaked, I guess, in a sense, it might look like a normal distribution, but it's probably not going to be I think we often jump to use a normal distribution for everything that looks at all curvy, but sometimes that's maybe not appropriate because a normal has a tail that will go to negative. Can P be negative? Can it be greater than 1? Does that really make sense? So I think it's quite nice to have in your toolbox as a practicing scientist, just a bit of a working knowledge of the really common distributions and what their domain are. So you know that a uniform distribution can go from one limit to another. A normal is from negative infinity to positive infinity. A gamma is from 0 to plus infinity. Beta is between two any numbers. And with those, you can probably always fit a distribution to any kind of prior if you just know what kind of mean do I want, what standard deviation do I want, and what kind of limits make sense.
Not only is it important to have that kind of toolbox of distributions and know about their ranges, like Connor's pointing out, but one of the really cool things that Bayesian land kind of taught me is all the deep relationships between those distributions. Like this distribution is the marginal of that distribution. If you have this prior, that this one, there's a bunch of interconnections between those relationships that you need the toolbox of probability theory, of Bayesian analysis to kind of grok those relationships. And it's very helpful.
Yeah.
At least it was.
It invokes lots of thoughts from me as well, because there are lots of interesting relationships between functions. When you study Fourier analysis, for example, you learn that the complex exponentials are basically trigonometric functions, and I'm sure the distributions are related in a similar way.
That's a good example.
Indeed. But the thing is, when we do neural networks, we just always use the ReLU activation function. And I just wondered, how fractionated is it? Because I would like to believe that the universe is quite homogeneous in its stochastic generating functions. And, I wouldn't need to go overboard in, looking at all of these different functions for doing things. How fractionated is it?
I don't think the normal distribution exists in nature nearly as much as we think it does, so much as the log normal does. And that's just a factor of time. Like you think about the size of, say, fish in the ocean would probably be a good example. Just a single species, that's not going to be normally distributed. For one, it's not going to go all the way to like negative sizes. So we can already say the assumptions of the normal distribution don't quite match. Okay, so why might we think log normal then? Well, because there's only going to be a very small amount of very, very small fish. That's actually probably going to be exponential, but whatever, we'll ignore that for now. There'll be very small amounts of incredibly tiny fish that are so small that it's birth defects and they're probably going to die. There's going to be a very large body of like spawn, and then that tail is going to go out longer and longer until you have a very tiny number of very large fish. And doing sort of like a lot of applied data analysis, I more often see these kinds of exponential tails with, some weird behavior down the bottom that are either gamma or log normal or one of these sort of 0 to infinity distributions, one of these long-tailed distributions. Then we see the normal distribution. The normal distribution does arise, but it tends to arise in situations where you ignore time. As soon as you add time to things, you tend to get power laws and exponential tails and all kinds of nasty stuff that mean, our nice assumptions about Gaussianity tend to completely break down.
So it reminds me of your point earlier about how hard it is to choose a good prior that is uninformative. I talk about normals and log normals. Have you heard of Benford's law? It came up quite recently in people talking about. So Benford's law is quite cool when you first come across it. If you look at a newspaper and you just write down every number you see, the date, the page number, anything, and you look at the first digit of that number, you'll find way more 1s, 2s, and 3s than you will find 7, 8s, and 9s. So the date, That starts with a 2. The year, sorry. The month probably starts with a 1. I mean, my height in centimeters, that starts with a 1. My age starts with a 2. So just numbers in general tend to start with a low digit. And that's often because you can think about it maybe as having you have a
distribution,
a prior that's in log space rather than in normal space. If you look at a log scale, multiple scales, a lot of that space is taken up with 1, 2, 3 rather than 8, 9, 10. So the distribution of all numbers in the world that we come across in life across multiple scales is probably like log normal distributed rather than actual normal distribution, actually distributed.
A quick point on that. When Greece joined the EU, they made up their numbers. They wanted to make it look like they were economically solvent. So they made up their numbers, and presumably they used a uniform random number generator, or they just made up some spreadsheets. And it was exactly that. It was the Benford law.
Is a little bit more sophisticated. Goldman Sachs is a little bit more sophisticated than the rand-n function in Excel, I'd like to think.
Well, who knows? But that was the proof, though, that they made up the numbers.
Yeah, they use Benford's law. At least in some countries, I don't know about all, but they do use it for detecting tax fraud because your digits, deviate from this distribution. I think it's it's funny to know how that law was discovered, which was this Canadian astronomer, I believe it was, Simon Newcomb, back in the day, right, when they wanted logarithms, they'd go look in a book. So there were these books that had tables of logarithms, so you could just kind of look those up, didn't have calculators. And he noticed that the pages on like the section for 1, were much more smudged than the ones like later in the book, and sort of that the smudging, decreased as you went to larger digits, like larger leading digits, right? And so he found that there was this distribution where, I think it's like the ratio between leading digit 1 versus 2 is the proportionality is basically, 1 over 1, 1 over 1 plus 1. So it's like 1 over, 1/2 as many are 2s, and then 1/3 for 3, that sort of thing. It's like 1 over n basically is kind of the distribution in a continuous space. And then if you integrate it between 0 and 1, 1 and 2, 2 and 3, you get the distribution for the leading digit. So it's essentially like Jeffrey's law, or Jeffrey's prior for ignorance, if you will. And so, people just discovered this through this natural phenomenon of smudging the paper more, like in the lower digits, right? I mean, these are real natural phenomenon that we see out there, and it occurs with like lengths of rivers, masses of fish, planets, etc. I mean, it's kind of an interesting, deep connection.
So what's the intuition? I could understand with sizes of apple, right, that the Gaussian is quite intuitive. But with numbers, there must be some kind of environmental rate limiting step that determines those kind of numbers appearing in our world. What is that?
So I'll give you my take on the intuition and then let the others give you theirs. So let me talk about the intuition behind Jeffrey's prior. So Jeffrey's prior says that, the ignorance distribution for a scale parameter, and it's important here that I'm talking about like kind of scale, is 1 over that scale. Okay, so like 1 over x, or 1 over, sigma, for example. Sigma is a standard deviation. Why that? Well, it turns out that, any power, if you use that distribution for 1 over sigma, then it's also the same ignorance distribution for 1 over any power of that. So if you're using sigma squared in your equations instead, the ignorance distribution is also 1 over sigma squared, because if you do the probability transformation correctly, you'll find out that that's how 1 over sigma would transform to sort of any powers. So it's a scale invariant, parameter. And so maybe it's saying something about kind of the universe as a whole, that it kind of has this scale invariance in the sense that like whatever units you choose for time, maybe we all decide tomorrow that we don't like seconds anymore. We're going to measure all our data in like 60-second, minute intervals or something like that. It doesn't matter what scale you choose to measure time. The scale that you choose to measure length is in a sense kind of arbitrary. And so if you want to make it to where it doesn't matter what yardstick you're using in lots of measurement situations, then you want a scale invariant kind of prior. And so maybe it's saying something deep about the universe has some kind of built-in kind of scale invariance. I mean, we know it does have like things like Lorentz invariance and other sort of, scale invariant type of properties. And it seems to have these kind of things that repeat at different scales. So I don't know the answer, but it's cool.
I think my intuition behind that one is that just that there's often not a really single obvious prior distribution that you should go for if you're ignorant. I think sometimes we have a knee-jerk reaction that the uniform distribution seems like just the best thing to do if you don't know any if you have no information, you want to be as ignorant as possible. But it's got this Achilles heel, the uniform distribution, because it's uniform over what? Over the variable, over log of the variable, over 1 minus the variable, it can make a difference. So one example is this. Consider two factories, right, that both make cubes, okay? And one factory A, makes cubes of length between 1 meter and 2 meters randomly. And the second factory, it produces cubes of volume between 1 meter cubed and 8 meter cubes. Now, are they the same factory? That's the question. So at first you might think, they're the same because, a cube with length 2 meters is the same as a cube of volume 8 meter cube. So they're the same. But then, well, if the first one is uniform between 1 and 2, then the average cube is of length 1.5. And that's a different cube to a cube of volume, 4.5. So uniform on length is not the same as uniform on volume. And it's how you phrase the question, what you mean by randomly between 1 and 2. Randomly was spent random with respect to x or x squared or x cubed. They're all different. And so you can't, I guess my takeaway from that experiment is that you can't just slap a uniform distribution on it and say, okay, that's my prior. I don't need to think anymore. Like it matters.
But what's the punchline there? Because the prior was the same on both, but are you saying that it's model building? So
the prior sounds the same, but it's actually a different prior. So a prior of uniform length between 1 and 2 is different to a prior of uniform volume between 1 and 8. So the reason it's a little bit different is that try to consider what would be in the middle. So a cube of, kind of just in my head, what is 1.5 to the power of 3? I'm not quite sure. But it's different to 4.5. So the second factory, it turns out on average, will produce bigger cubes than the first. And the priors only superficially sound the same, which is what makes that kind of a interesting thought experiment.
Yeah, I'm going to offend both our guest and Keith here by saying pick whichever distribution makes your numerical integrator happy, because MCMC, HMC is hard enough. No, look, it's kind of a cop out, but if you think of it, as just a constraint on the numerical integration, so that your chains don't run forever before you get a sufficient number of samples to actually do something with your data, then then you can motivate it with pragmatism, and it doesn't feel so much of a cop out. Like I've never understood the appeal of scale invariance. Abstractly, it's a cool principle, but in practice, it's scale invariant for a particular choice of model. I'm gonna probably pick a great big normal. I'm a big fan of Andrew Gelman's work, and him looking at what he calls weakly informative priors, which is say we scale our data to like 0-1 normals, or standard input scaling. We subtract out the mean, divide by the standard deviation. In theory, we have our data sitting with somewhere within one standard deviation for the most part. We then put a prior with standard deviation of like 5 or 10 over our parameters, much bigger than we'd actually expect the effect size to be. In that case, what we're doing is we're not saying anything specific about the data. We're saying we think the parameter is probably going to be normally distributed, but we're not sure. But more importantly, what we're not doing is we're not integrating from minus infinity to infinity.
Yep.
Now we're integrating in a much more targeted range, and that much more targeted range makes the problem tractable if you have some kind of model with a weird, topology, like these hierarchical models we discussed earlier. Philosophically, they're a fantastic idea. Practically computing them is basically the entire motivation of the Stan programming language, because there's these weird numerics when you get deep down to how these things actually work.
One thing that's interesting, and we were kind of talking about just the kind of magical theoretical connections that were kind of quite interesting, and then you jump to pragmatism, which I love because I'm a pragmatist, right? So what's kind of interesting about the kind of Bayesian, people who come from a Bayesian direction and head towards pragmatism is because they're kind of forced to think about these integrals all the time. They essentially just go, all right, forget it. Like, I'm just going to write down whatever kind of practical model I can, and just in some way that I can numerically integrate it, right? And the nice thing about that is it lets you throw in everything scientifically, because you can just, like, for example, for a long time, I would actually, to every single model I would add to it an alternative model with a low prior probability that was just uniform everywhere, like essentially a 5% chance of something I never expected happening, right? Because I found it was important to have that anomaly, sort of anomalous model in there, right? Like, I'm going to allow for anomalous data points, essentially. And you can just throw in the whole kitchen sink, like almost like Erai's approach to building a general intelligence. Let's just throw in everything, and then we got to do this numerical integral anyway. And like we kind of mentioned earlier, the priors, maybe they're worth one data point or two or a half or whatever. The important part is the likelihood function and doing the integrals. So I'm totally on board with that approach, but I do like thinking about where these sort of deep connections, may lie with the underlying magical universe. Go ahead, Tim.
Well, yeah, I mean, that's super interesting, but it is interesting from my point of view as a naive bystander that I assume that a lot of Bayesian approaches are about sample efficiency and updating your prior beliefs and reasoning under uncertainty and so on. But a big part of it, as Alex was saying, is just wrestling with the computational complexity of solving these numerical integrations. And these are clearly situations where if you increase the specificity of your prior, you're just massively cutting down the space of possible solutions that you need to be searching in effectively. But just with an eye on the time, I wanted to get into model building and some of these numerical integration approaches.
Oh boy, that's a can of worms. I think for the sake of not blowing out the time, can we just agree that like variations on MCMC and sequential Monte Carlo are cool, and there are various cool approaches, and then maybe move on to model building from there? Because otherwise, we'll be here all night.
Well, could you succinctly describe what is going on? Let's say Markov Chain Monte Carlo. What is it?
Connor, do you want to do this one, or I'm happy to give it a crack? But you've got the maths background, literally and metaphorically.
Sure, I'll give that one a crack. So Markov Chain Monte Carlo is a really cool, really useful technique, but it's a bit wacky the way it works. I was surprised when I first heard it, like actually that it's a thing we have to do that actually works, but it's gold dust. I think it's useful because often in Bayes' theorem, we have the prior times by the likelihood divided by the evidence. And often we can't compute the evidence. So it's a term, maybe it's intractable, maybe it's computationally really hard to do. And so we have this posterior distribution where we know what the nominator is, but we don't know what the denominator is. So we know it up to a kind of a constant factor. And so we're most of the way there, but we can't really say how likely any particular prediction is. But what we can do is we can compare the relative likelihood. And the way I think about MCMC is that it gives you a tool to go from an unnormalized posterior probability distribution and still work with it, still get results out. And so you have a particular regime for generating samples and moving to a new area and accepting or rejecting samples as a chain, as a Markov model. And you can use a whole variety of different ways of moving around your space of in your probability distribution. And if you leave it running for long enough, you'll end up with a sampling distribution that is a good approximation for the full distribution. So it's a really useful thing to have. Then the challenge that comes with it, the thing that makes it quite annoying, is you can never know for sure whether you've run the chain for long enough. It needs to be burnt in, and it might be, for example, you're stuck in one particular area of your sample space, and there's another area you've never explored. And you can do all these diagnostics, but fundamentally, you can tell when you haven't, run it for long enough. There are things that go wrong. But it's really hard to tell when you have run it for long enough. You can never be sure that you're not missing something enormous.
This is one of the big problems. With any optimization problem, multimodality. Most systems just break when they encounter multimodality. And I've seen some research. A friend of mine was working on some stuff involving a thing called the shadow Hamiltonian. And from how I remember him describing, this is all way over my head, but from how he was describing it, it was a system designed to exploit the energy function, which is kind of like the Hamiltonian, which is kind of equivalent to the unnormalized probability density. So, like, instead of how do we put this? Instead of just looking at the ratio of our two samples, we instead model the probability space as this unnormalized probability density and send our sample, so to speak, we simulate it as an ODE and just send our sample swinging around this energy surface in random directions. And that will give us draws from this like normalized probability density. But there are the point to all of that is there are techniques that exploit joules of that particular problem to try and handle multimodality better. But in the end, multimodality is this really hard problem that unless you've got these nice unimodal distributions that our samplers can just walk up, you're in the same place as everyone else in statistics and machine learning. You're stuck in local optima.
Right. So I wonder if we can expand out of the kind of theory and math just for a little bit. And I'm curious, you as a practitioner, actually all of you for that matter, how is the kind of, let's say, social context of Bayesianism these days? Because I remember, so back when I was kind of, let's say, more involved in the community, late 90s, early 2000s, something like that. It was very firmly entrenched kind of frequentism. I mean, there was the kind of maximum entropy conference you could go to and kind of meet other Bayesians, and but kind of the Bayesian approach, if you will, was really more of a niche thing in areas where you did have small sample sizes and the stakes were very high. So an example would be military targeting systems. I can't tell you how many people from DoD funded research I ran into at the kind of Bayesian conferences or corner table or whatever. And I kind of gotten the sense that over the last maybe 10 to 15 years, that somehow or another kind of the machine learning community has started to, become a bit more open to Bayesian methods, or more people are taking them seriously or exploring them. I'm wondering if you can just comment a bit on that if that's an actual change, or if I'm just seeing things, or kind of what the current state of this type of thinking is.
I think, you're absolutely right.
Not just the machine learning. Yeah, but it's not just the machine learning community. It's all through science. And I don't want to speak too long on the subject because Connor's probably more deep into that. But I definitely point to things like the replication crisis and the failure of statistics as practice for the last sort of 50 or so years as really pushing people to look for alternatives. And Bayesianism is essentially, now it's computable. Everyone's got a computer and everyone can run a sampler.
Sure. I mean, sometimes it's dramatized as a revolution that's taken over the world, but there's definitely been a really big shift. I think in science, I think it's a good example, particularly in medical sciences, where it's really important that statisticians can present some results in a way that is easily understood. So going back to what we're talking about with confidence intervals, it just makes sense to to share with someone a Bayesian interval where their instinctive understanding is going to be of a Bayesian interval, rather than a weird frequentist interval that we can have to train people really hard to interpret it perfectly. But in machine learning, I think it's a little bit different. I think a lot of data scientists, you can use a model without understanding how it works and understanding anything about the algorithm under the hood. In the same way that you can drive a car very safely and get to work without knowing anything about how an engine works or how a clutch works. And so I think a lot of people have started using Bayesian methods just because from an applied perspective, they found out that they worked really well. And then maybe a bit later on, they might do a bit of digging and say, well, what's really going on here? And why are we doing this? But definitely becoming a lot more accepted.
Are there some areas where Bayesian approaches are more acceptable? And I would imagine that for something like computer vision, for example, Bayesian approaches wouldn't work very well. And I now need to update my position on that because we spoke to Max Welling last week, and they are indeed building computer vision models using Gaussian processors. But the reason they're doing that is there are situations in computer vision where you are irregularly sampling images, right? And you might not have access to the entire image data. And also you might be sampling images irregularly or not on gridded data. So having Gaussian processors there to represent the image data can be beneficial. But this all seems a little bit esoteric to me. I mean, presumably most people would just use CNNs, right?
I think so. But nonetheless, even if no matter what model you use, I think if you can always fit that into a probabilistic framework, right? So Bayesian statistics is kind of quite synonymous with this normal probability theory these days, as Keith was saying. So that you can take any classifier that works anyway and treat it as a likelihood, or treat it as a discriminative model that gives you a conditional probability of y given x. But no matter what you use as your discriminative model, as your conditional probability, you can still overall think about a problem in a Bayesian context by, as a second step, incorporating some other information and using prior probabilities. So I think there's no reason you can't think like a Bayesian whilst using any traditional technique.
Yeah, I think that's really key. I think for 90% of problems, your first pass is always frequentist, if only just because it's quicker to calculate. You can quickly call some functions, calculate some central tendencies. You don't need to spend hours waiting for a sampling process to complete. You can get some ballpark, high level summary statistics of your data, enough to kind of give you a clue of where to look and what sort of model you might want to be doing. And there's nothing wrong with that. There are certainly cases where you're not going to be doing 100-dimensional integrals because that's just madness. Like that way insanity and very high cloud compute costs lie. So there's nothing wrong with applying frequentist techniques. They're a great first approximation. When you need something fast, go frequentist. When you need something done properly, do it the Bayesian way, because that way you get the right answer. You get the right answer in the information that you need. But generally, that's the last step.
Yeah, and I agree with you there, which is my first step when I was doing kind of research, if you will, was always actually visual. Like I wanted to make some plots, let me plot this by this and a cloud plot, heat map, whatever, in order to reduce the dimensionality enough so that my feeble human mind, which can sort of barely grasp maybe 3 or 3+1 dimensions, could handle. I would have to do some type of first pass statistical summarization and a whole bunch of different sort of plots. So then I could zero in on, here's some interesting structure that maybe I can try and think about more and model. So absolutely. And actually, Connor, you'll appreciate this. I didn't start off knowing about Bayesian things either. I was from the same, orthodox kind of background. And at some point in my past, I was trying to calculate the lifetime of fluorophores from very small photon counts, like 23 photons or something that I would collect from a sample, right? And I was looking at these plots of things, and I could kind of tell with my eye what the lifetime would be roughly of that fluorophore, some exponential decay plot or whatever. But I needed a quantitative measure for that. So I'm out looking up white papers, trying to figure out how to incorporate the prior knowledge we had into into this. How many photons do you need to measure a lifetime of a fluorophore? And I literally found a paper called "How Many Photons Do You Need to Calculate the Lifetime of a Fluorophore?" And it goes through this whole Fisher information, blah blah blah, whatever analysis, and comes to some conclusion that like you need 10,000. And I was like, well, shit, I've got like 30 or less. Like, what do I do now? Like, how do I do research now? And it just so happened that a office mate of mine, and this is one of these weird coincidences in life. I'm sitting here looking at this paper, and this office mate he's laughing over at his desk, just laughing. So I'm in a dead end. I get up, I walk over. Hey, Mike, what's so funny? Oh, I'm reading this book about, sort of statistics. And I'm just laughing at this chapter that's talking about how like orthodox statistics totally breaks down and yet you can still solve the problem with like Bayesian maximum likelihood or something. I'm like, can I see that book for a minute? I grab it, and it's Data Analysis, a Bayesian Tutorial by Civia. And it completely changed my life because it gave me a tool set to deal with these small sample count kinds of problems where I could incorporate the physics knowledge that I had from, what was going on. But I'm just saying, I don't disagree with you, Alex. Like, as a first pass, visualization techniques, and those require reduction and dimensionality, go for it. And then, like you said, when you actually need to model something and incorporate your scientific knowledge into that process and or get the most you can out of a small number of data points, you have to embrace these tools.
It reminds me of I think I remembered when I first heard about Bayes' theorem in a lecture at university. We were learning about neutrinos, which are really cool things, right? They're tiny elementary particles, and they pass through you all the time. They don't interact very much, and they're one of the most exciting things to look at for quantum, for particle astrophysics, because they were created very early on in the universe. So about the cosmic microwave background using photons. Well, neutrinos are even better because they let you see even further back in time. But anyway, someone did an experiment, and they were measuring how fast neutrinos travel. And it rocked the world. It was about in 2013 or so. And they realized that neutrinos actually traveled faster than light under at very specific circumstances. They'd recorded it, they had the data, they made a distribution, and they had all their random and systematic errors captured. And
I think I remember this.
This was it's really cool, right? It's so exciting. We love it when we break our previous physics models, because then we can do some more research.
Yes.
We love it. We love it. The worst thing is when you get a result that is exactly what you predicted, because that's just so boring and you can't do anything else. And everyone was chatting about it. And in a lecture, a professor of physics was saying, okay, so I'm going to show you a theory today that explains why I will bet any money that they've made a mistake somewhere in their experiment, that they're wrong. Even though there's no hint of any kind of issue with the experiment so far. And so, drew it down, and he pointed at the prior and said, look, we've got decades and decades and decades of nothing ever going faster than the speed of light. It's just so unlikely to happen. Even though they've got evidence at like the 2 or 3 sigma level, still on the balance of probabilities, much, much more likely that they've just made a mistake somewhere. And then lo and behold, a few weeks later, it's like, oh, they hadn't quite plugged in something correctly. It was that bad. Yeah. So, and he was right. So,
yeah. Bayesians can win a lot of money through gambling. That's something to know.
Could I touch on something else as well? Because Alex made the assertion that Bayesian methods are slower, so only do it if you've got lots of time and lots of compute. But that's not always true. Bayesian optimization is quite an interesting one. So if you're searching through some parameter space, this irregular sampling thing is really interesting because you can just kind of focus your effort where you need to be focusing your effort. So is that an example of where a Bayesian approach will actually improve the time it takes to find the optimum parameters? Well,
it can certainly. So if you're extracting more out of every data point because you have you're able to incorporate your physical knowledge into the situation, then you can absolutely arrive at accurate answers with, say, smaller sample counts. As far as the actual computations, I think it's really just, let's put it this way. A lot of, say, frequentist results are things that you would derive by following a Bayesian approach if you made all the same assumptions. Like, I'm going to assume Gaussians and uniform priors and blah, blah, and I end up with the same, it's telling me to do the same calculation. It's just that in a lot of scenarios, it's telling you to do some kind of, nasty integral, right? And the MCMC we mentioned earlier, that's a very general purpose technique for sampling probability distributions where you can calculate the likelihood, but you can't calculate the normalized likelihood, but you have a function that can give you back, the likelihood. Then it provides you with a way of kind of, let's say, semi-efficiently sampling, from that distribution. And there are even ways to make it better. Like if you know some kind of approximation of the distribution, then you can kind of skew the sampling that gets fed into like the Metropolis Hastings sample or the Gibbs sample or whatever, and then you can calculate some results and then unskew them, back to what would have happened if you'd have sort of sampled properly. But they're very general purpose techniques. They may be widely deployed in kind of a Bayesian context because it requires you to do these integrals. Yeah.
I don't know if one of you could talk me through this Bayesian optimization example, but that's quite intuitive, isn't it? So I have a regression model and I have 6 parameters. I want to optimize the parameters to find, to have the lowest loss or something like that. And the alternative would be to do a grid search. And that's a fairly exhaustive search. And I'm going to be searching in lots of places where I don't need to be searching. Whereas presumably I could model it as a kind of Gaussian process, and I could model some kind of dependency between all of those variables. I would define some sort of prior on all of the different parameters, and that should allow me. Now, would I still use Markov Chain Monte Carlo for that?
I think Bayesian optimization, I don't think that uses MCMC, but it's a really cool trick though, if you're building an ML model. It's great if you're doing searching over a space of hyperparameters that's huge, and you want something more efficient and more guided than just a grid search or a random sample.
The big thing there is, again, a Gaussian process it's just an interpolation technique that gives us uncertainty. So if we suspect that an area may have a higher, we don't just have to sample randomly and hope that we explore the space. We can look at the areas where we're most uncertain and put samples right down there so that we can check how that affects our predictions across the entire space. That's kind of really the magic of Bayesian optimization. But the computations there are still slow. So if you were to have that on an inner loop on, we had a bit of a giggle a couple of weeks ago about the inner optimization loop on that capsule, on Hinton's capsule nets using expectation maximization. If you were to put these calculations in there, it would suddenly get much slower because we're putting all these very heavy calculations in. And this is kind of where Bayes being slow is kind of a misnomer. It's often quicker to get to the answer, the information that you're looking for, because you integrate things like your uncertainty. You summarize all of your knowledge. You don't just take point estimates of it. However, getting to that point where you can make decisions, where you can act on that information, it is often much more difficult. And these are the issues of sampling and the issues of Bayesian optimization. These are kind of two, or Bayesian, hyperparameter optimization. These are two kind of distinct beasts that kind of need to be looked at from different perspectives because they involve different things.
I think Bayesian optimization is probably the thing that's going to get me fired first.
Oh, why is that?
I think it's really powerful for automated machine learning, which is there are these automl tools I'm sure you've heard about that try to automate more of the job of a data scientist rather than just training a classifier, but maybe feature engineering, maybe model selection. And Bayesian optimization is, I think, a really key part of doing that job well. One of the things that humans can do a bit better than machines. So using Bayesian optimization for the task of searching over the space of different ML models and their hyperparameters is, I think, one of the things that's kind of making AutoML slowly start to catch up with the data scientist in that particular. So I'll give you an example of what I mean.
Yeah.
When you're searching for hyperparameters of an ML model, then a basic approach is a grid search. So you take every possible combination of every possible parameter in a giant grid. That's fine if it's 2D, it's like 2D lattice. If you have 10 or more parameters, they can get really big. So then you can do a random search where you define a distribution over every dimension you want to search over, and then you just take take 50 samples from that, and then try them out and score your model based on that. And then Bayesian optimization is the next level. It's even better. So you fit a Gaussian process model or something like that on your set of hyperparameters and how well they've done, and then that guides you of where's a promising space to try next. And you can trade off exploration and exploitation. So your optimizer might say something like, well, we've tried a lot of regularization and it's been quite good, but we haven't run any models with very little regularization. So let's try one or two over there. So it's a lot more intelligent, it's a lot more human, and a lot more efficient if you have a model that takes a long time to run, like a big neural network.
So there are different approaches. So you could use a genetic algorithm, for example, and that's a very similar thing. So it will maintain a population of interesting parameters. You could presumably do some kind of convex optimization, but it wouldn't work very well because you have kind of categorical parameters. And I suppose the first point I wanted to make is that with these automated machine learning solutions, with classical machine learning, the hyperparameters aren't that important. The algorithms aren't even that important. It's the featureization which is the most important. So technologies like H2O, the most innovative thing they do is creating features. So they do all sorts of different encodings and different combinations of features and so on. And then, of course, they'll try different algorithms, different hyperparameters. But it seems to be the features which is the most important thing.
So regarding the genetic, algorithm versus Bayesian optimization, if by that we're talking about kind of the classic, genetic optimization where you start off with some type of random sampling within the hyperparameter space, and then you sort of allow those points to evolve, right, and they'll sort of naturally approach the local optimum that are nearest their kind of starting position. Is that what you're talking about? Like that type of approach? So the advantage of Bayesian or the theoretical advantage of Bayesian optimization, if you will, is that because you have this surrogate function, which we haven't talked about before, but in Bayesian optimization, what you're doing is let's say you're overlaying on top of the hyperparameter space a model. Okay, and that model is this surrogate function that we kind of think sort of allows us to represent the objective function, right, in that space. And let's say it's a Gaussian, process model. It's going to have a smoothness to it, which allows the points to influence each other. And that's kind of the hypothetical advantage that they have over just kind of the points wandering around in isolation, is that they can sort of have this smooth, n squared effect on each other because you're building up this underlying model. Of course, if the surrogate function is very far from the structure of the objective function, then it can be a hindrance, as well. But it just turns out that, in a lot of the problems we work on in these hyperparameter spaces, they are kind of like these multimodal, relatively smooth sort of Gaussian process systems. So that was the point I wanted to make there. And then as far as the feature regularization or feature construction goes, I don't disagree with you at all. I do just want to kind of put a little caveat in there, which is that there's some arbitrariness there between the distinction between a feature versus a parameter, because there's a lot of models in which the parameter space can actually define what you might call features elsewhere. Like, for example, if I have a model that allows an unknown number of modes, like in some type of multimodal distribution, like I have a hyperparameter that says allow for there to be n Gaussians, like in this mixture or whatever. You can think of those Gaussians as features because one of them might combine variables sort of in a different way to end up with what might traditionally have been a feature. So there is a bit of a kind of general sense in which these are all the same thing, like hyperparameters, parameters, features. They can all be kind of in a very general sense a part of a very complex model, if you will.
Well, you said they could combine them in an interesting way, but the obvious example is computer vision. So there is a spatial relation between the pixels, and So a CNN has an inductive prior that models local connectivity between the pixels.
Exactly. So in the case of great example, so say just a classic CNN in computer vision, a channel is a feature, right? And so if I have a hyperparameter that says I have some number of channels, 6 channels, 24 channels, that hyperparameter actually becomes a feature engineering parameter, if you will, because it allows itself to introduce, new features in there. So I just want to say there are contexts in which, in which features can be a part or can be a part of the hyperparameter, space, if you will, or specification.
Yeah, I think you're saying they can be expressed as a function of the hyperparameters.
Yeah.
Well, we're nearly at time. Connor, do you have any advice for aspiring data scientists that want to get more into the world of Bayesian?
Oh, that's a good question. Probably the best thing I've read in Bayesian stats that really helped pull everything together for me in data science was Daphne Koller, who's a Stanford professor. She has a massive book called Probabilistic Graphical Models. And it's more of a reference thing. You wouldn't want to read it all at once. But it really opened my eyes to how everything that I'd ever learned in machine learning, I could describe as, fitted into that framework somewhere. Maybe think some things were generative models, some things were discriminative models, and then ideas of Bayesian networks as a way to, an awesome tool to combine expert knowledge and then also learning some data. It's so incredibly powerful. And it's such a great thing because you can slot into that framework everything that you already know. So I think learning about probabilistic graphical models, you don't often hear them talked about too much in machine learning, but I think they're the best thing since sliced bread. They're so cool. And I wish there were better open source packages to support it, so we wouldn't have to write so much code ourselves. But they're the coolest thing, I think. In fact, I've got a puzzle.
Go on.
A little optimization puzzle that I sometimes ask people if they're starting as a data scientist. So I want to see what you make of it. Okay, so it's quite a simple one. It's like an optimization one. Might be an interview question. Okay, so you work in a factory that produces mobile phones, okay? And this factory has 100 floors. And you want to determine what height you can drop the phones from such that they won't break. And you can do an experiment by dropping a phone out the window and just seeing if it breaks. And then presumably sending someone downstairs to pick up the pieces and coming back. So you could just throw a phone out every window. And maybe someone's thrown a phone off the roof and it definitely breaks, and someone's put it on the ground and it definitely doesn't break. So it's somewhere in that range. And you wish to minimize the expected number of experiments that you have to do until you've determined the highest floor from which the phone won't break when dropped. So what's your strategy for which floors do you try?
I would imagine you'd have some kind of a distribution over the floors. And I'm guessing clearly on the early floors, it probably won't break. And then I would imagine it would kind of increase exponentially, right? Well, exponentially is the wrong word, but it would kind of curve up.
What most people would do before hearing about Bayesian stats, and I guarantee this is the answer you get 90% of the time, is people will say, I've solved it. Use a binary search tree. You go floor 50, and then maybe if it's above 75, and then floor 62, and you halve each time, and then 2 to the 7. So you should always be able to do it in 7 experiments or less. That's the most efficient. They've forgotten their prior. They've completely forgotten their prior knowledge.
They've forgotten the kinetic energy prior.
It's almost definitely going to break from the first floor. So you just do it in 1, right? Like check out the first floor. If it doesn't break, throw it out the second. It will definitely break then. But when presented with that setup, people forget their prior immediately.
I think my value function's broken. I just want to set up a conveyor belt off the 100th floor and see what happens. See how smashed things can get.
Yeah, I've got a new iPhone. I'm not going to be chucking this out of any windows.
No. I have a question for you, Connor. Who do you think we should interview next? Who would you like to see on Machine Learning Street Talk?
Oh, that is a good question. I think Professor Daphne Koller would be the most incredible guest to have if you could get her from Stanford.
Cool.
Okay. Well, we're going to make it happen.
Suggestion.
Yeah,
and when we get Daphne on, you can take my spot, Connor.
I'll just be gushing the whole time.
Amazing.
Well, her book is amazing.
I have actually come across, I came across Daphne on Twitter the other day. This is a coincidence, but there was a guy at DeepMind who said, "Oh, like everyone else, he wasn't educated. Exactly, he wasn't educated by Andrew Wang and all these new founded courses. He, read Chris Bishop and Daphne Collar. I'm sure he said that. So I did actually download that PDF a couple of days ago, and it's fantastic. It's free to download, isn't it? I think.
I think so, yeah. And she's also, I think, a co-founder of Coursera, like Andrew Ng. So she's a great educator.
Wow. Amazing. Well, Connor Tann, thank you very much for joining us this evening. It's been an absolute pleasure.
Thank you very much for having me.
Amazing.
Thank you.